Hello students, welcome to Diksha Karnataka YouTube channel. In this video, I'm going to discuss the top 30 questions in electric charges and fields. Okay, so here these 30 questions are repeated in KCET. Okay, I mean if you look at the previous year question paper, so this top 30 questions, these questions are repeated. Okay, so if you are able to solve these 30 questions, so then it is assured that you will be able to solve these kind of questions in KCET exam. Question number 1. When 10 to the power 19 electrons are removed from a neutral metal plate, the electric charge on it is. Okay, so this is the metallic plate. Okay, metallic plates. So they removed 10 to the power 19 electrons, right? 10 to the power 19 electrons. That is n equal to 10 to the power 19 electrons from the neutral metal plate. Okay, so we need to find electric charge on it is. So when you remove the electron from the metallic plate, so what happens? This metal plate will be positively charged, right? Isn't it? They remove the electrons, so it becomes positively charged. So now the charge on the metallic plates is equal to n times charge on the electron, charge of the electron, right? So this is from the quantization of charge, right? Isn't it? So now Q is equal to 10 to the power 19 into what is the charge of the electron, magnitude of the charge of the electron, 1.6 into 10 to the power minus 19 coulomb, right? So the value of Q, that is the electric charge on the metallic plate, Q is equal to 1.6 coulomb. Okay, 1.6 coulomb, positive 1.6 coulomb. So option A is the correct answer. Okay, yeah. Next question. Question number 2. The electrostatic force between two charges of 10 microcoulomb and 20 microcoulomb at a distance of 2 microcoulomb is to be halved. This can be affected by. Okay, so here Q1 is 10 microcoulomb. Okay, Q2 is 20 microcoulomb, right? So this is Q2. Okay, Q2, and D is 2 micrometer. Okay, so the force between this 10 microcoulomb, that is Q1, and Q2, that is 20 microcoulomb, and at a distance of 2 micrometer is to be halved. Okay, so this can be affected by. Okay, so here the original force, that is force between 10 microcoulomb, 20 microcoulomb at a distance of 2 micrometer, F equal to, so let us find the force between them. Okay, F equal to 10 microcoulomb. So K is 1 by 4 pi epsilon naught, K into 10 microcoulomb into 20 microcoulomb, that is 200 into 10 to the power minus 12 coulomb square, divided by D square. D square is 2 micrometer whole square. So 2 micrometer whole square is 4 into 10 to the power minus 12. So 10 to the power minus 12, 10 to the power minus 12 will get cancelled. So F equal to 200 by 4, right? So 200 by 4 is 50, right? F equal to 50K. 50K. Okay. So now here we need to check every option, right? So it is to be halved, right? So the first one, the force is to be halved, right? So the first one, reducing both charges by 50%. Okay, so let us see. Here I'm going to use another slide. Okay, so now the force F dash, okay, F dash is equal to, here this can be affected by reducing both charges by 50%. Okay, I'm checking the option A. Okay, so now F dash is equal to K into Q1 by 2, right? Q1 by 2. So I'm reducing the both charges by 50%, right? Isn't it? That is half of each charges. So Q1 by 2 into Q2 by 2 divided by, distance is not changing, right? So it is D square only. Okay, so F dash is equal to here K by 4 into Q1 Q2 divided by D square. So here K Q1 Q2 divided by D square is 50K, right? So F dash is equal to 50K divided by 4, right? So this is 1 by 4th of the original force, right? Or the initial force, right? Isn't it? So here it is to be halved. So option A is wrong, right? So let's check option B, reducing both charges and their separation each by 50%. Okay, let's check the second option. Okay. So now F dash is equal to K Q1 by 2 Q2 by 2 divided by, here we are reducing the distance, we are also reducing the distance by 50%, right? So that is d square by 4, right? D by 2, that is d square by 4. D by 2 whole square is d square by 4. Okay. So here F dash is equal to K Q1 Q2 divided by d square into, here 1 by 2 into 1 by 2 is 1 by 4. So 1 by 4 will get cancelled, right? So it is 1. So F dash is equal to K Q1 Q2 by d square is 50K, right? Here this one, K Q1 Q2 by d square is 50K. So F dash is equal to F. The force is same. If you reduce the charge by 50% and distance by 50%, you will get the same force, right? So option B is also wrong, right? So let's check option C. By doubling one of the charges and doubling the separation between them. Okay. So here we are doubling one of the charges, right? So F dash is equal to, I'm going to double the charge Q1, that is 10 microfarad. Okay. So this is Q1 and Q2, right? I'm going to double the charge Q1. So F dash is equal to K into 2 Q1 then Q2 divided by, and double the distance also, right? So if you double the distance, then it will be 2d, right? Square of 2d is 4d square, right? So F dash is equal to, here 2 by 4 is 1 by 2. So K Q1 Q2 divided by 2d square, right? K Q1 Q2 divided by d square is F, right? Isn't it? So F dash is equal to F by 2. See, here F is halved, right? Isn't it? Force is halved. So to be halved, that is, the force is to be halved by doubling one of the charges and doubling the separation between them. Okay. So option C is the correct answer. Understood? So here you have to check every option. Okay. So in exam, yeah. Next question. Question number 3. Two identical metal spheres with charges 2q and minus q are separated by distance d. Force between them is F. Okay. So here two identical metal spheres with charges 2q and minus q. Okay. These two are separated by a distance d. Okay. Force between them is F. That is F equal to K into 2q into q, the magnitude of the force. Okay. K into 2q into q divided by d square. That is F equal to, here 2k q square divided by d square. They are connected by conducting wire and then removed. Okay. So these two are connected by one conducting wire. Okay. Conducting wire and then removed. Force between them now is, okay, so when you connect the two charged metal sphere, what happens? There will be a charge distribution, right? So the charge on each sphere will be Q1 plus Q2 divided by 2 and Q1 plus Q2 divided by 2, right? So the charge on 2q sphere, right? The charge on the first sphere. So this will be Q1 plus Q2 by 2. Q1 is 2q, Q2 is minus q. So Q1 plus Q2 is 2q minus q, that is q only, right? So q by 2, right? So the charge on first sphere is q by 2, charge on second sphere is q by 2. After connecting the wire and then removed, right? The distance between them is d only. So now we need to find the force between them, right? So now the force between them, F dash, is equal to K into Q by 2 into Q by 2, Coulomb's law, right? K into Q by 2 into Q by 2 divided by d square. So F dash is equal to here KQ square divided by d square into 1 by 4, right? Isn't it? Here KQ square divided by d square is equal to F by 2, right? So from this equation. So now F dash is equal to F by 2 into 1 by 4, that is F by 8. So the correct option is B. Okay. Yeah. Next question. Question number 4. The electric force between two point charges separated by a certain distance in air is F. Okay. Here there are 2 point charges. Okay. Q1 and Q2 separated by distance, let's say d, in air is F. Here the force between them is F. The distance at which they should be placed in a medium of relative permittivity K. Here epsilon r is K. Okay, so that the force remain the same. Okay, so when it is in air, the force between them is F, right? So F is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by d square, right? So this is the force between the two charges when it is placed in air at a certain distance d, right? So now it is placed in a medium, right? With the relative permittivity, the relative permittivity of the medium is K. Okay. The force remains the same, right? So we need to find the distance, the new distance, right? Isn't it? So F dash is equal to 1 divided by 4 pi epsilon naught into K Q1 Q2 divided by d square, right? So this is the force between the two charges when it is placed in a medium, right? Here the force is same, right? F dash is equal to F. F dash is equal to F. Okay, here we need to find new distance, right? So let's say d1 square. Okay, d1 square. 1 divided by 4 pi epsilon naught into q1 q2 divided by d1 square. So F dash is equal to 1 divided by 4 pi epsilon naught into k q1 q2 divided by d1 square is equal to F is 1 divided by 4 pi epsilon naught q1 q2 by d square, right? So 1 divided by 4 pi epsilon naught q1 q2, okay, q1 q2 divided by 4 pi epsilon naught, here q1 q2 divided by 4 pi epsilon naught will get cancelled, right? So we need to find d1, right? So d1 is equal to root of d square divided by k. So d1 is equal to d divided by root k. Okay, so the correct option is D. Yeah, next question. Question number 5. A certain charge Q is divided into two parts, small q and Q minus Q, capital Q minus Q. What is the relation between Q and Q of the two parts placed at a certain distance apart are have maximum force of repulsion? Okay, here this charge Q is divided into two parts, small q and capital Q minus Q, right? Okay, so this is Q and capital Q minus Q. Okay, so these two are separated by certain distance, right? These two are separated by certain distance D. So here we need to find the maximum force. Okay, sorry, we need to find the value of charge. Okay, so when the force of repulsion is maximum, right? Isn't it? So this is the distance d where the force of repulsion between the q and capital Q minus q is maximum, right? So here first we have to write the force equation using Coulomb's law, then differentiate with respect to q, then equate that into 0, then you will get the relation between capital Q and small q. Okay, yeah. So now here the force between these two charges q and capital Q minus q. So now F is equal to K, that is 1 by 4 pi epsilon naught, into Q into capital Q minus q divided by d square, right? So now we need to differentiate F with respect to q. So now dF divided by dq, isn't it? Differentiate F with respect to small q, okay? dF divided by dq, then equate that into 0. Now d divided by dq of, here F is K into small q into capital Q, right, minus small q into small q, that is q square, whole divided by d square, right, equal to 0. So now what is the differentiation of small q into capital Q with respect to small q, that is capital Q only, right? Q minus, what is the differentiation of small q square with respect to small q, that is minus, sorry, 2q only, q minus 2q, which is equal to 0, right? K divided by d square will go to the other side, so it becomes 0, right? So now q equal to capital Q equal to, here capital Q equal to 2 times small q. So the correct option is D. Okay, yeah. Next question, question number 6. An infinite number of charges, each of charge 1 microcoulomb, are placed on the x-axis with coordinates x equal to 1, 2, 4, 8 and so on infinity. If a charge of 1 coulomb is kept at the origin, then what is the net force acting on 1 coulomb charge? Okay. Y-axis, x-axis, right? Here 1 coulomb charge is kept at the origin, right? And then infinite number of charges, each of charge 1 microcoulomb, are placed on x-axis with coordinates x equal to 1, 2, 4, 8 and so on, right? So x equal to 1, the charge 1 microcoulomb is placed, right? And then x equal to 2, the charge 1 microcoulomb is placed and so on. And next x equal to 4, charge 1 microcoulomb is placed and so on, right? So we need to find net force on 1 coulomb charge, right? Okay. So now what is the force on 1 coulomb charge due to 1 microcoulomb? So let's say F1. F1 is the force on 1 coulomb charge due to 1 microcoulomb. So F1 is equal to K. K is 1 by 4 pi epsilon naught into Q1. Q1 is 1 coulomb, okay, into 1 microcoulomb, that is 10 to the power minus 6 coulomb, divided by d square. D square is distance between origin, here 0 and 1, that is 1 only, right? Take 1 meter, okay, 1 meter, 2 meter, 3 meter, sorry, 4 meter and so on. 1 meter, 2 meter, 4 meter, 8 meter and so on, okay? So this will be 1 square. So F1 is equal to, here 10 to the power minus 6 into K only, right? Isn't it? So this is F1. Let's find F2, that is force on 1 coulomb due to 1 microcoulomb on 2 meter. So which is lying on x-axis, right? So F2 is equal to K into 1 coulomb into 1 microcoulomb, that is 10 to the power minus 6, divided by the distance between origin and 2 meter, that is 2 meter only, right? So 2 square is 4, so 4, okay? So now F2 is equal to 10 to the power minus 6 divided by 4 into K, okay? So now similarly F3 is equal to follow the same method, you will get here 10 to the power minus 6 into k divided by 16, right? Isn't it? F4 is 10 to the power minus 6 divided by 64 and so on. So now we need to find net force. Net force equal to summation of all the forces, right? So F1 plus F2 plus F3 and so on, right? So now F net is equal to, here take k into 10 to the power minus 6 as common, right? So k into 10 to the power minus 6 as common. So now here this will be 1 plus 1 by 4 plus 1 by 16 plus 1 by 64 and so on, right? Isn't it? So this is infinite series, right? So what is the formula for infinite sum? Here S is equal to A divided by 1 minus R. What is A? A is the first term, R is common term, right? So common term is 1 by 4, right? First term is 1. So S equal to 1 divided by 1 minus 1 by 4. 1 minus 1 by 4 is 3 by 4, right? 1 by 3 by 4 is 4 by 3. So S equal to 4 by 3. S equal to 4 divided by 3, right? So now F net is equal to, K is 9 into 10 to the power 9, right? That is 1 by 4 pi epsilon naught. The value of 1 by 4 pi epsilon naught is 9 into 10 to the power 9 into 10 to the power minus 6 into 4 by 3. Okay, 3 3s are 9, right? So 3 into 4 is 12, right? 10 to the power minus 6 into 10 to the power 9 is 10 to the power 3. So 12 into 10 to the power 3 is 12,000, right? The net force is 12,000 Newton. Net force on 1 coulomb charge, okay, is 12,000 Newton. So option B is the correct answer. Understood? Yeah. Next question. Question number 7. 2-point charges of plus 0.1 microcoulomb each are placed at a separation of 0.2 meter in air. Okay. So here 2-point charges plus 1 point microcoulomb. Okay. Plus, okay, here plus 0.1 microcoulomb. Okay. Plus 0.1 microcoulomb and plus 0.1 microcoulomb are separated by distance 0.2 meter, that is 20 centimeter in air. The electric field strength at a point midway between the two charges is. Here we need to find electric field at a point which is lying on the midway between the two charges, right? So the distance between point P and 0.1 microcoulomb, right, at point A. Here this is point A and point B. Okay. So the distance is here 0.1 meter, and again here the distance is 0.1 meter also, right? The distance between point P and B. So now the direction of the electric field at point P due to 0.1 microcoulomb at B is towards right, and the direction of the electric field due to 0.1 microcoulomb which is placed at point A is towards right. So this is towards left. Okay. The direction of the electric field due to 0.1 microcoulomb at B is towards left, and the direction of the electric field due to 0.1 microcoulomb at A is towards right. So both are in opposite direction, right? And the magnitude of the electric field is same, right? Isn't it? So magnitude of the electric field is same. E is equal to K into charge Q, that is 0.1 microcoulomb divided by distance squared, right? 0.1 squared, right? So at point P, electric field due to B, right? Electric field due to charge at B is also same, right? Both are in opposite direction. So the electric field will cancel each other. So the net electric field at point P is equal to 0. So the correct option is C. Okay. Yeah. So you don't need to solve this question. Okay. So whenever two same charges, okay, magnitude is same. So two charges, same sign and same magnitude, okay, separated by certain distance d, then the electric field at the midpoint between them is 0. Okay, understood? Electric field between these two charges, that is the same charges, is 0. Uh, but here, okay, electric field is not 0. Understood? If the sign is negative, okay, if the sign is negative, so then where is the electric field is 0? So you have to figure it out. Okay, so write the answer in comment box. Yeah. Next question, question number 8. A cube of side B has charge Q at each of its vertices. Okay, we have cube of side B, right? And charge Q, charges, okay, charge Q's placed at each of the vertices, right? Here Q, 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 and Q. Okay. The electric field at the center of the cube will be. Electric field at the center of the cube will be. Okay. So this one is dead easy one, right? So how to solve this one without using any formula and all? See here, the direction of the electric field. Okay. Before that, let's name each vertices. Okay. So this is A, B, C, D. Okay. Now E, F, G, and H. Okay. So now electric field at the center of the cube due to this charge Q on B is in this direction, right? That is, the direction is towards this Q or towards E, right? Now the direction of the electric field due to this charge on E, right, is towards B. The value of the charge is same, right? Magnitude is same, right? So electric field, the direction of the electric field is opposite, right? So these two will get cancel each other, right? So then similarly, the electric field directing towards F is cancelled by electric field directing towards A, right? And here electric field directing towards D is cancelled by electric field directing towards G, right? Isn't it? So all electric field will get cancel each other, right? So the net electric field at the center of the cube is 0. So the correct option is D. Okay. Yeah. Next question. Okay. Question number 9. A charged oil drop is suspended in a uniform field of 3 into 10 to the power volt per meter so that it neither falls nor rises. The charge on the drop will be. Okay. So this is the drop. Okay. Mass of the drop is M. Okay. Mass of the drop is equal to M. M is 9.9 into 10 to the power minus 15 kg. Okay. So it is at equilibrium, right? Here it is suspended in a uniform electric field, right? So E is equal to 3 into 10 to the power 4 volt per meter, right? So it is at equilibrium, right? Isn't it? Mass of the charge is given. So the gravitational force is acting on this oil drop, right? So it is in downward direction, right? And the electric force acting on this oil drop is in upward direction, right? That is Q into E. Q is charge of the oil drop, okay? So it is at equilibrium, that is the force, electric force is cancelled by the gravitational force, right? Or electric force is equal to gravitational force, right? So then only the oil can attain equilibrium position, right? Or equilibrium, right? Okay. So now QE is equal to mg, right? We need to find the value of Q. So Q equal to mg divided by E. That's it. So now you need to substitute the values of mg and E. So now Q is equal to M. M is 9.9 into 10 to the power minus 15 kg. Okay. into G. G is 10 meter per second square divided by E. E is 3 into 10 to the power 4 volt per meter. So this will be 3.3 into 10 to the power minus 15 into 10, that is 10 to the power minus 14 divided by 10 to the power 4. 10 to the power minus 14 divided by 10 to the power 4 is 10 to the power minus 18, right? So the value of charge Q is equal to 3.3 into 10 to the power minus 18 coulomb. So the correct option is C, right? Yeah. Next question. Question number 10. A charged particle of mass m and charge q is released from rest in a uniform electric field. Neglecting the effect of gravity, the kinetic energy of the charged particle after t second. Okay. So charged particle of mass m, okay, mass m, charge q is released from rest in a uniform electric field. Okay, in a uniform electric field. So this is the direction of the electric field. Okay, uniform electric field A. So we have to neglect the effect of gravity, the kinetic energy of the charged particle after t seconds. Okay, so because of this electric field, the charged particle will accelerate, right? So it will get accelerated. So now here after time t, what is the velocity of the particle, right? After time t, what is the velocity of the particle? So that one we need to find, right? So if you find the velocity of the particle after time t, so then we can easily find the kinetic energy, right? So what is kinetic energy? Half mv square, that's it. So now here, what is the value of the v after time t? So now apply first equation of motion, right? Everybody knows the first equation of motion, right? V equal to u plus at, right? Here the charged particle of mass m, charge q released from rest, right? That is initial velocity is 0. So v, that is final velocity or velocity at time t, after time t, v equal to a into t. Okay, we need to find t, right? So here we need to find a. Okay, so using electric field, charge q and mass m. So how to find a, that is acceleration of the charged particle? Here the charged particle will get accelerated, right? Accelerated. So F equal to m into a, Newton's second law of motion, right? Here the direction of the F is in horizontal direction towards right, isn't it? So what is the force? This force is Q into E, electrostatic force, right? Electrostatic force is equal to m into a. So now a equal to Q into E divided by m. Okay, so now V is equal to a is QE by m into t, right? Okay, now we have found the velocity of the charged particle after time t. So now find kinetic energy, right? So now kinetic energy is equal to half into m into v square, that is q square e square divided by m square into t square, right? So we need to find t, right? So now t is equal to, sorry, here we need to find kinetic energy only, right? Isn't it? So m will get cancelled, right? M will get cancelled. M will get cancelled. So the kinetic energy is equal to q square e square t square divided by 2m. That's it. Here we need to find kinetic energy, right? After time t. So the correct option is D. Okay, understood? Yeah. Next question. Question number 11. Among the following, the correct graphical representation of variation of electric intensity as a function of distance from the center of a uniformly charged conducting spherical shell of radius r having total charge q is shown is, okay, so this is the spherical shell, right? Conducting spherical shell. So the charge of the spherical shell is q. The radius of the spherical shell is r, capital R. Okay. Now what is the electric field at point P? Here the point P lying outside the spherical shell, right? The distance between the center of the spherical shell and point P is r. Okay. So now electric field at point P is equal to k into capital Q divided by r square, right? E is equal to k into capital Q divided by r square, right? So this is the case when point P lying outside the spherical shell, right? R is greater than capital R, right? Isn't it? And then the point P lying on the surface of the spherical shell, then electric field R equal to capital R. Electric field on the surface of the spherical shell is equal to K into Q divided by capital R square, right? And then electric field inside the spherical shell is 0, right? Electric field inside the spherical shell is 0. So now we have to draw E versus R graph, right? Isn't it? Or we have to take the correct option of the E versus R graph. Okay. Here, from the center of the spherical shell to the surface of the spherical shell, electric field is 0, right? Electric field is 0. On the surface of the spherical shell, electric field is kq by r square, right? Kq by r square. So then, outside the spherical shell, the electric field is kq by small r square, right? It decreases like this. Here E is inversely proportional to small r square. Okay, so the correct option is B. Okay, so this is the correct graph. I hope everybody understood. So this one is direct question. Okay, so they will ask in CET, they will ask these kind of questions. So question number 12. Two parallel large thin metal sheets have equal surface charge densities. Sigma is surface charge density. Okay, sigma equal to 26.4 into 10 to the power minus 12 coulomb per meter square of opposite signs. The electric field between these sheets, okay, this is the two parallel large thin metal sheets, okay, have equal surface charge density but opposite signs. Okay, so we need to find electric field between these sheets. Okay, so electric field due to negative sigma, that is this sheet. Okay, this is the sheet B and sheet A. Electric field due to sheet B is towards right, isn't it? So electric field due to negative plate, okay, or negative sheet is equal to sigma divided by 2 epsilon naught, right? Sigma divided by 2 epsilon naught. It's in magnitude. And electric field due to positively charged plate, so that is E plus sigma is equal to sigma divided by 2 epsilon naught, right? So these two electric field both are in same direction, right? So you have to add it. So net electric field is equal to 2 sigma divided by 2 epsilon naught. So 2 will get cancelled. So electric field between these two plates is sigma divided by epsilon naught, right? So the value of the sigma is given, right? And value of the epsilon naught, here, value of the epsilon naught is 4 pi, right? 4 pi into 9 into 10 to the power 9, right? 10 to the power 9. And then what is the SI unit of the epsilon naught? SI unit of the epsilon naught is here 1 by epsilon naught, right? So this is equal to Newton per coulomb square. Okay, Newton meter square per coulomb square, right? Newton meter square per coulomb square, right? Okay, so here E equal to sigma is 26.4 into 10 to the power minus 12 into 1 divided by sigma is 4 pi into 10 to the power 9 into 9. Okay, so now 10 to the power 9 into 10 to the power minus 12 is 10 to the power minus 3, right? So 10 to the power minus 3 into 4 pi, 4 pi into 9 is 36, right? So 26.4 into 36 pi, right? So now solve this, okay? Solve this, you will get answer 3 Newton per coulomb, okay? E equal to 3, approximately equal to 3 Newton per coulomb. So the correct option is C. Okay. Yeah. Next question. Question number 13. 27 identical drops of liquid carrying equal charge coalesces, that is combined, to form large drop. Here 27. Okay, 27 drops. So it coalesces and combine to form larger drop, right? Large drop. So let's say the radius of the large drop is r, okay, and radius of the smaller drop is smaller, okay. The electric field on the surface of the large drop is dash times the surface of the small drop. Here Es is the electric field on the surface of the smaller drop, okay, electric field on the surface of the smaller drop, okay. Yeah. So here the volume of the 27 drop is equal to volume of the larger drop, right? So from that we can find the relation between small r and capital R, right? So volume of the larger drop is equal to 27 times volume of the smaller drop, right? So volume of the larger drop is 4 by 3 pi capital R cube, right? Equal to 27 times volume of the smaller drop is 4 by 3 pi small r cube, right? So now solve this, you will get r equal to capital R, sorry, small r into 3, right? So small r is equal to capital R divided by 3, okay. So now what is the electric field on the larger drop? El is equal to K into the total charge. Total charge is 27 times Q, okay. So let's say Q is the charge, the single charge or the charge on the smaller drops, okay. So K into 27 times Q divided by capital R square, right? Es is the electric field on the surface of the smaller drop or small drop, which is equal to K into Q divided by small r square. Small r is R by 3, capital R by 3. So Es is equal to here 9 KQ divided by capital R square. So now divide EL by ES. So EL divided by ES is equal to 27 times KQ divided by capital R square divided by 9Q divided by capital R square. So here KQ by R square will get cancelled. 9 3s are 27. So EL is equal to 3 times ES. Okay. So the correct option is B. Okay. Yeah. Next question. Question number 14. The electric field at a point due to an electric dipole and axis inclined at an angle theta, which is lesser than 90 degree, to the dipole axis if the angle theta is, okay. So here this is dipole, okay. So this is point P, okay, point P. The electric field at a point P due to an electric dipole, an axis inclined at an angle theta to the dipole axis. So this is the angle theta, okay. This is the angle theta. So which is, so it is to the dipole axis, right? So this will be P cos theta, right? And this will be P sin theta. I am dividing this P in two parts. One is P cos theta and P sin theta. So we need to find the angle, this angle theta, okay. So now this point P is on or is lying on the axial line of the P cos theta, this dipole, right? Isn't it? isn't it? So what is the direction of the electric field? This way, right? Electric field due to P cos theta on P is in this way, right? So let's say this is E1, okay? And what is the direction of the electric field due to P sin theta? It is in this way, right? Or perpendicular to E1. Why? Because this point P is lying on the equatorial line of the P sin theta, right? Isn't it? So this is E2, right? So now E1 is equal to 2 kp cos theta divided by r cube, right? So r is the distance between this point, okay, here, this point and point P, okay, and E2 is equal to kp sin theta divided by r cube, right? So this is the net electric field. Here the net electric field is making an angle alpha with the E1, okay? So this is the net electric field. Understood? So now here tan alpha is equal to E2 divided by E1, right? Isn't it? E2 divided by E1. Yes or no? So now tan alpha is equal to E2 is kp sin theta by r cube. E1 is 2 kp cos theta by r cube, right? So now I can write it as tan theta divided by 2, right? Tan theta divided by 2. So now here alpha, the value of alpha is 90 minus theta, right? So this angle is alpha, right? So this angle will also be alpha, right? So this alpha is equal to 90 minus theta, right? So tan 90 minus theta is equal to tan theta by 2, right? Tan 90 minus theta is equal to tan theta by 2, right? Tan 90 minus theta is cot theta, right? Cot theta is 1 by tan theta, right? So here tan square theta is equal to 2, right? So theta equal to tan inverse of root 2. That's it. So the correct option, that is the value of angle theta, is equal to tan inverse of 2. So the correct option is B. Okay. I hope everybody understood how to solve this problem. Okay. Simple one, the direct one. So I am doing all this derivation. In exam, you don't need to derive all this thing. Okay. You don't need to derive all these things. So you should remember this standard formula. Okay, this is the standard formula. Yeah. Next question. Okay, question number 15. Two charges 4q and q are 3x apart in air. A charge q, that is capital Q, is placed at a point on the line joining so that the system of these three charges remains in equilibrium. Here 4q charge at point A and small q charge at point B are separated by distance 3x, okay, and another charge q is placed at a point on line joining so that the system of these three charges remains in equilibrium. Okay, here then the distance of q, capital Q, from 4q and the value of qr. Your distance between 4q and capital Q is d. Okay, so we need to find the value of d and we need to find the value of q. Okay, yeah. So here the whole system remains in equilibrium, right? That is, this q is also in equilibrium, right? It is not moving. That is, the force acting on this capital Q charge due to 4q, okay, let's say F1, is cancelled by force acting on capital Q charge due to small q charge, that is F2, right? So then only F can be in equilibrium, right? Isn't it? So let's write F1. F1 is equal to 4q into capital Q the product of two charges into proportionality constant, that is 1 by 4 pi epsilon naught, which is equal to k divided by d square, right? This is F1, and F2 is equal to here k into q divided by d minus 3x whole square, right? Okay, F1 equal to F2, right? F1 is equal to F2. So F1 is here 4k small q into capital Q divided by d square is equal to k q divided by d minus 3x whole square, right? So now solve this, you will get the value of d as 2x. Okay, so the distance between 4q and capital Q is 2x. Understood? Okay, so now we have to find the value of capital Q, right? Okay, the whole system is in equilibrium, so the net force is 0, right? Net force is equal to 0, right? So net force is equal to force acting on capital Q due to 4q, and F2, the force acting on capital Q due to small q, and F3, the force acting on small q due to capital 4q. Sorry, for small q due to 4q. That's it. So F1 plus F2 plus F3, which is equal to 0, right? We know F1, F2, right? Isn't it? F3 is k into 4q into q divided by 3x whole square, right? Okay. So now F1 is here k q into 4q divided by distance between 4q and q is 2x, right? So 2x whole square is 4x square plus F2. F2 is here q into k divided by here 2x, 3x minus 2x, that is x. So x squared plus F3. F3 is here the force between 4q and q. So k 4q square divided by 3x whole square, that is 9x square, which is equal to 0. Okay, so now solve this. Here you will get the value of q as minus 4q divided by 9. Sorry, minus 2q divided by 9. Minus 2q by 9. So the correct option is A. Okay, yeah. Next question, question number 16. Two small spheres, each having the charge plus q, are suspended by insulating threads of length L from a hook. This arrangement is taken in space where there is no gravitational effect. Okay, so here the two small charges, okay, are suspended by insulating threads of length L, okay, from a hook. So this is the hook. So this arrangement is taken into a space where there is no gravitational effect. Okay, G is equal to 0. Acceleration due to gravity is 0. Then the angle between the two suspensions and the tension in each will be, okay. So when there is no gravitational effect, the angle between the two suspensions is equal to 180 degree, right? There is no gravitational effect, right? Isn't it? So it will be 180 degree, right? 180 degree, right? Okay, so option B is eliminated, right? Here we have to choose the correct option between A, C and D. Okay, so the angle is 180 degree. The suspension angle is 180 degree. Okay, so now we need to find the tension between these two threads, right? The length is L and L. Okay, so both are charged, right? The charge is plus Q. So now what is the repulsive force between these two charges? The repulsive force between these two charges is K into capital Q square divided by 4L square, right? So this is the repulsive force between these two charges. So which is equal to tension in the thread, right? Isn't it? So angle 180 degree and the tension F equal to T, okay? So which is equal to KQ square divided by 4L square or 2L whole square. So the correct option is A. Okay, yeah. Next question, question number 70. A cube of side 2 centimeter has charge of 12 microcoulomb, then the surface charge density is, okay. So here the surface charge density sigma is Q divided by A, right? Q divided by A. So Q is given, right? Isn't it? Q is 12 microcoulomb, right? So we need to find surface charge density sigma, right? So what is A? A is surface area of the cube, right? So what is the surface area of the cube? Surface area of the cube equal to 6 times area of the one side, right? Isn't it? Area of the one side or area of the one face, not side, area of the one face. Here this is cube, right? This is cube. So surface charge density sigma is equal to the charge 12 microcoulomb, right? And the surface area of this cube, right? So 6 into surface area of one face, right? So now the value of sigma is equal to 12 microcoulomb, 12 into 10 to the power minus 6 divided by 6 into the side is 2 centimeter, right? Isn't it? So 2 into 10 to the power minus 2 into 2 into 10 to the power minus 2, right? So 2 into 2 is 4, 4 into 6 is 24, right? So sigma equal to 12 divided by 24 is 1 by 2. So 1 by 2 into 10 to the power minus 6 by 10 to the power minus 4 is 10 to the power minus 2. So 1 by 2 is 0.5, right? 0.5 is 5 into 10 to the power minus 1. 10 to the power minus 1 into 10 to the power minus 2 is 10 to the power minus 3. So 5 into 10 to the power minus 3 coulomb per meter square, right? So the correct option is B. Okay, understood? Yeah, next question, question number 18. 3-point charges are placed at the corners of an equilateral triangle, assuming only electrostatic forces are acting. So here 3-point charges Q1, Q2, Q3 placed at the corners of an equilateral triangle, right? L and L and L. Yeah. Assuming only electrostatic forces are acting. So option A says the system will be in equilibrium if the charges rotate about the center of the triangle. Here the system will not be in equilibrium, right? So it cannot be in equilibrium, okay, if the charges are placed at the corners of the equilateral triangle, okay? So option A is wrong. Option B, the system can never be in equilibrium. Correct. The system can never be in equilibrium. Okay. So option B is the correct answer. Okay. Yeah. Next question. Question number 19. Two identical charged spheres of material density rho suspended from the same point by inextensible strings of equal length make an angle theta between the strings. Okay. So here two strings, okay, inextensible strings, the length of the two strings are same, okay. So it is making an angle theta between the two strings. Here the angle is theta, right? When suspended in a liquid of density A, the angle theta remains the same. Here this whole system is immersed in the liquid of density A, okay, and angle theta remains the same. The dielectric constant K of the liquid is, okay, so we need to find dielectric constant of this liquid, okay, yeah. So now how to find? the dielectric constant, right, using the given data. So here, when it is placed in air, right, here the whole system is placed in air, right. So the gravitational force acting on both sphere is mg, right, identical sphere mg. The tension on thread is T, right, here the angle is theta, right. So we have to resolve T, right. So this will be T cos theta by 2, right. So this is theta by 2 and theta by 2. So T cos theta by 2 and T sin theta by 2, right. The whole system is in equilibrium, right, in air. So this T sin theta by 2 will be cancelled by the electrostatic force or the force on this sphere due to this charged sphere, right, the force on this charged sphere due to this charged sphere. So this is Fe, right. The same thing for this charged sphere also, Fe T cos theta by 2 and T sin theta by 2, T sin theta by 2, right. Okay, so now apply Newton's second law of motion, right. So T cos theta by 2 is equal to mg, right. T sin theta by 2 is equal to Fe, right. So tan theta by 2 is equal to Fe by mg, right. Tan theta by 2 is equal to Fe by mg. Okay, here angle remains same, right, when you immerse the whole system into a liquid, right. Okay, so now tan theta by 2 is equal to the force between these two charged spheres is Fe by k, right, Fe by k divided by, so now we need to find the gravitational force, right, isn't it, or the net force in downward direction. Okay, so when you placed these two or the whole system is in medium, so what happens, there will be a buoyant force, right, it is in upward direction, right. So here the buoyant force is A, that is density of the medium into volume of this ball or the sphere into g, right, and the gravitational force is mg, right. M is rho into v, so rho into v into g, right. So the now net force in downward direction or the vertical direction is rho vg minus a into v into g, right. Okay, so now tan theta by 2 is equal to Fe divided by k divided by rho vg minus a into v into g. Okay, so now tan theta by 2 is equal to Fe by mg, right, Fe by mg. So Fe divided by m is rho into v into g, mg, right, which is equal to Fe divided by k into rho vg minus a into v into g. Okay, Fe will get cancelled, right. So we need to find the value of k, right, that is the dielectric constant of the medium. So k is equal to rho divided by rho minus a, that's it. Okay, rho divided by rho minus a. So the correct option is D. Okay, so do the calculation part. Okay, so you will get the correct answer, k equal to rho divided by rho minus a. Yeah, next question, question number 20. In the uniform electric field of E equal to 1 into 10 to the power 4 Newton per coulomb, an electron is accelerated from the rest. Okay, so here this is the uniform electric field of 10 to the power 4 Newton per coulomb. Okay, and electron accelerated from the rest. Okay, electron accelerated from the rest. The velocity of the electron when it has travelled a distance of 2 into 10 to the power minus 2 meter is nearly. Okay, electron travelled a distance of 2 into 10 to the power minus 2 meter. Okay. Here electron reached at this point. This is the point B and point A. Okay. So we need to find the velocity of the electron at point B. Distance between A and B is 2 into 10 to the power minus 2 meter, that is 2 centimeter. Okay. Yeah. So first we need to find acceleration of the electron, right? First we need to find acceleration of the electron, then apply third equation of motion. From that you will get the value of the velocity, right? Okay. So now the third equation of motion is v square equal to u square plus 2as, right? U is 0 because electron accelerated from the rest, right? U equal to 0. So v equal to, or v square equal to 2as. So v equal to root of 2 into a into s. Okay. Now let us find a, that is acceleration of the electron when it is traveled the distance 2 into 10 to the power minus 2 meter. So the electron got accelerated, right? So F equal to m into a, Newton's second law of motion, right? So F is electric force, right? Electric force Q equal to m into a. So now a equal to QE by m, right? So now velocity v is equal to root of 2 into a. A is q into e divided by m into s, right? So now substitute the values. Root of 2 into q is charge of the electron 1.6 into 10 to the power minus 19 coulomb divided by m. M is mass of the electron 9.1 into 10 to the power minus 31 kg into s. S is distance traveled by the electron 2 into 10 to the power minus 2 meter. Okay. So now solve this, you will get v equal to 8.5 into 10 to the power 6 meter per second. Okay. 8.5 into 10 to the power 6 meter per second. So the correct option is B. Understood? Yeah. Next question. Question number 21. An electric dipole consists of two opposite charges, each of 0.1 microcoulomb. Yeah. Electric dipole consists of each opposite charges minus q, which is equal to here 0.1 minus 0.1 microcoulomb, right? So this is the plus q, that is 0.1 microcoulomb. So minus q and plus q. The value of q is 0.1 microcoulomb. Okay. Minus q means minus 0.1 microcoulomb. Yeah. So it is separated by 0.03 meter. Okay. So it is separated by 0.03 meter. The dipole is placed in a uniform electric field of 2 into 10 to the power 6 Newton per coulomb. Okay. So this is the direction of the electric field. Okay. So now we have placed this dipole in a uniform electric field. Okay. The value of the electric field is given 2 into 10 to the power 6 Newton per coulomb at an angle 30 degree with the field. Here at an angle 30 degree with the field, right? The torque exerted by the field on the dipole is, we know the formula, right? The torque exerted on the dipole when the dipole is placed in a uniform electric field is P cross E, right? Torque vector is equal to dipole P vector cross electric field vector E vector. So in magnitude, tau equal to P into E sin theta, right? Theta is angle between electric field and dipole, right? So now tau equal to the dipole moment, P is Q into D, right? Isn't it? Q into D into E sin theta, right? So now substitute the values, that's it. So now tau equal to Q, that is 0.1 into 10 to the power minus 6 into D, that is 0.03 into E is 2 into 10 to the power 6 into sin theta. Sin theta is 1 divided by 2, sin 30 degree. Sin 30 degree is 1 by 2. So here 2 will get cancelled, right? So now tau is equal to 3 into 10 to the power minus 3, 3 into 10 to the power minus 3 Newton meter. The SI unit of the torque, tau is Newton meter, right? So tau equal to 3 into 10 to the power minus 3 Newton meter. So option B is the correct answer. Okay. Yeah. Question number 22. A proton and an alpha particle are accelerated in the same uniform electric field. Their accelerations are in the ratio. Okay. So both are accelerated in a same uniform electric field, right? Isn't it? So the electric force is equal to m into A, right? F equal to m into A. So F is electric force, right? So now A equal to Q into E divided by M. Okay. So Q is the charge of the particle, right? Here proton and alpha, right? So now let Qp be the charge of the proton. So Q alpha is equal to 2 times Qp, right? 2 times Qp. That is Q alpha is charge of the alpha particle, right? Now Mp is the mass of the proton. Okay. So M alpha is equal to 4 times Mp, right? That is 4 times mass of the proton. Now we need to find the ratio of the acceleration of the proton to acceleration of the alpha particle. So which is equal to here Qp into E divided by Mp whole divided by Q alpha into E divided by M alpha. So now AP divided by A alpha is equal to Qp divided by Q alpha is 2 times Qp, okay, into M alpha divided by Mp. M alpha is 4 times Mp divided by Mp. So Mp, Qp will get cancelled. 2 2s are 4. So the ratio AP is to A alpha is equal to 2 is to 1. So the correct option is B. Okay. Yeah. Next question. Question number 23. An electron of mass m, charge E, falls through a distance h meter in a uniform electric field E. The time of fall is, okay. So this is the direction of the electric field. Okay. The electron of mass m, charge E, falls through a distance h in a uniform electric field, right? So this is point A and point B. The distance between A and B is h. Okay, we need to find the time of fall. So how to find time of fall? Apply second equation of motion. Okay, second equation of motion is S equal to ut plus half A into t square. See here, we have to neglect the gravitational effect. Okay, so they didn't tell us we have to consider the gravitational effect. Okay, so we can neglect it. So now here u is 0, right? Initial velocity is not given, so u is 0 and s equal to h, right? I can write this equation as h equal to here h equal to half A into t square. H equal to half A into t square. Okay, so this is h equal to half A into t square. So now we need to find t, right? So t equal to root of 2h divided by A. Okay, so now we need to find the value of A, right? That is acceleration of the electron when it is moving in uniform electric field. Okay, moving in a uniform electric field. So now the force experienced by the electron F equal to E into capital E, right? Small e is charge of the electron into capital E is electric field, right? So it is accelerated, right? So this F is equal to m into A. So E into E equal to m into A. So A is equal to small e into capital E divided by m. So now substitute the expression of m to this equation. So now T is equal to root of 2hm divided by charge of the electron into electric field. So the correct option is B. Okay, T equal to root of 2hm divided by E into E. Yeah. Next question. Question number 24. the force experienced by a charge plus 3 microcoulomb placed at the midpoint P on the line joining the two charges is. Yeah. So this is the given diagram, right? So plus 3 microcoulomb charge is placed at point P, right, on the line joining the two charges. Okay, so we need to find force experienced by this 3 microcoulomb charge, right? Here the force on 3 microcoulomb charge due to this 3 microcoulomb charge, so let's say this point is A, this 3 microcoulomb charge is placed on A, and this is the point B. Minus 6 microcoulomb charge is placed on point B. So now force experienced by 3 microcoulomb charge on point P due to 3 microcoulomb charge on point A, right? So we have to apply Coulomb's law, right? Isn't it? So F equal to K into Q 1 into Q2 divided by D square. D is 6 meter, right? 6 meter. This is D. Yeah. So now F is equal to K is 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 into Q1. Q1 is 3 microcoulomb. So 3 into 10 to the power minus 6, right? 3 into 10 to the power minus 6, not 10 to the power minus 9, 10 to the power minus 6 into Q2. Q2 is 3 into 10 to the power minus 6 coulomb, right? K into Q1 into Q2 divided by D square. D square is distance between A and P, that is 2 meter. Sorry, 3 meter, right? Half of 6 is 3, so 3 meter. So 3 square is 9, right? So here 9 will get cancelled, right? 10 to the power minus 6 into 10 to the power minus 6 is 10 to the power minus 12. So 10 to the power minus 9, sorry, 10 to the power 9 into 10 to the power minus 12 is 10 to the power minus 3, right? So F, okay, let's say this is F1. So F1 is equal to 9 into 10 to the power minus 3 Newton, right? So this is the force between 3 microcoulomb charge on P due to 3 microcoulomb charge on A. Okay. So what is the direction of this force? The F1 is towards right, isn't it? F1 is towards right. Okay. So let us find force between or force on 3 microcoulomb charge, okay, due to minus 6 microcoulomb charge. That is F2. F2 equal to, use the same formula, K is 9 into 10 to the power 9 into Q1. Q1 is 3 into 10 to the power minus 6 coulomb into Q2. Okay, I'm going to take the magnitude of the Q2. Okay, in this case Q2 is minus here 6 microcoulomb charge, the magnitude of the Q2. Okay, so 6 into 10 to the power minus 6. Okay, divided by D square. D square is 3 square, that is 9, right? So 9 will get cancelled. 6 3s are 18. So F2 is equal to 18 into 10 to the power minus 3 Newton. Okay. So now what is the direction of the force? The direction of the force is also towards right, isn't it? So this is F1 and F2. So both forces are in the same direction, right? So we have to add up. So the net force on 3 microcoulomb is equal to F1 plus F2, right? So net force is equal to, F1 is 9 into 10 to the power minus 3 Newton, okay? So 9 into 10 to the power minus 3 Newton plus F2 is 18 into 10 to the power minus 3 Newton. Okay, so 9 plus 18 is 27. So net force is equal to 27 into 10 to the power minus 3 Newton. So the correct option is A. Okay, yeah. Next question, question number 25. What is the nature of Gaussian surface involved in Gauss law of electrostatics? The direct question, right? So here Gaussian surface is the imaginary closed surface around the charge, right? Isn't it? So it's a 3-dimensional space, right? So the nature of the Gaussian surface is vector, right? It is a vector. So the correct option is B. Question number 26. If there are only one type of charge in the universe, then E is electric field vector, ds is area vector. So let's look at the options. Option A, loop integral of E dot ds equal to infinity if charge is inside. Wrong, right? So according to Gauss's law, loop integral of E dot ds is equal to q enclosed, that is the total charge enclosed by the surface divided by epsilon naught. This is the Gauss's law, right? So it is inside, okay? Inside, outside, outside, loop integral of E dot ds is equal to 0, okay? So the second option is also wrong, right? The third option, loop integral of E dot ds equal to 0 if charge is outside, correct, right? If charge is outside, here, if charge is outside, loop integral of E dot ds equal to 0 and q by epsilon naught if charge is inside, correct, right? So option C is the correct answer, okay? Understood? So this one is a direct question, right? Isn't it, from the Gauss's law? Yeah. Next question. Question number 27. An infinitely long, thin straight wire has uniform charge density of 0.25 into 10 to the power minus 2 coulomb per meter. So that is the value of lambda is equal to 0.25 into 10 to the power minus 2 coulomb per meter. Okay. So this is linear charge density. What is the magnitude of electric field at a distance 20 centimeter from the axis of the wire? Okay, so this is the wire, okay, and here this is the point where we need to find the electric field, 20 centimeter, right? So this is the point P where we need to find the electric field, okay. Here this is uniformly charged wire, right? So what is the electric field at point P? The electric field at point P is E equal to lambda divided by 2 pi epsilon naught r, right? Electric field at point P due to uniformly charged wire is lambda divided by 2 pi epsilon naught r. Epsilon naught is permittivity in free space. R is the distance between the point P where we need to find electric field and the axis of the wire. So here E is equal to, now multiply and divided by 2. So this will be 2 lambda divided by 4 pi epsilon naught r. Now 1 by 4 pi epsilon naught is 9 into 10 to the power 9, right? Now substitute the values, then remaining values lambda and r. That's it. So now electric field E is equal to 2 into lambda. Lambda is 0.25 into 10 to the power minus 2 coulomb per meter, right? Into 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 divided by r. R is 20 centimeter, that is 20 into 10 to the power minus 2. So 10 to the power minus 2, 10 to the power minus 2 will get cancelled, right? So now 2 by 20 is 1 by 10, right? So now 9 into 0.25, that is 2.25, right? So 2.25 into 10 to the power 9 by 10 is 10 to the power 8. 10 to the power 8 Newton per coulomb, okay? 2.25 into 10 to the power 8 Newton per coulomb. So option A is the correct answer. Understood? Yeah, this one is also direct question, right? Direct formula based question. Yeah. Next one, 28. An electric dipole is kept in non-uniform electric field. It generally experiences a torque for not a force. Actually, this has to be a torque and not a force, okay? It will experience a torque, right? But the electric field is non-uniform, right? Isn't it? So it will also experience force, okay? If it is uniform electric field, then the net force is equal to 0, right? Okay, let's see the force, okay? Force acting on the electric dipole. So when it is placed in non-uniform electric field, right? So what is the potential energy of the dipole? The potential energy of the dipole is minus of P dot E, P is dipole moment, E is electric field vector, right? And the force is equal to negative gradient of potential energy, right? Negative gradient of potential energy. So now F is equal to minus d by dx of P into E, right? So this has to be minus P E cos theta. Here theta is angle between P and E, okay? So which is equal to 0 degrees. So dF equal to minus d by dx into d by dx of P into E, okay? So now F is equal to, here minus P into E, not just P into E, minus P into E. So now minus into minus plus, so P into dE by dx, right? See, here from this expression, we can conclude that the dipole experiences force, right? It will experience torque as well as force. So option A is wrong. Option B, a force and torque, correct, right? Option B is the correct answer. Okay? Yeah. Next question. Question number 29. 3-point charges plus 2q plus 2q and minus 4q are placed at the corners A, B and C of an equilateral triangle ABC of side X. Okay. So let us draw the equilateral triangle of side X. Here minus 4q is placed. Here plus 2q is placed. Here plus 2q is placed. Okay. So here this is A, this is B and C. Okay. The magnitude of the electric dipole moment of this system. Okay, we need to find magnitude of the electric dipole moment of the system, right? So the dipole moment along CA, right? Here the first one is dipole moment along CA and the second one is dipole moment along CB. Okay, so it's an equilateral triangle, right? So 60 degree, 60 degree and 60 degree, isn't it? So now this is the net electric dipole moment, right? So now the net electric dipole moment is equal to, net electric dipole moment is equal to, here P, so it is along CA, okay, P it's along CA, right, into cos 30 degree plus dipole moment P along CB cos 30 degree. So now net electric dipole moment in magnitude, okay, which is equal to, here the magnitude is same, right, along CA and CB. So P, right, P into cos 30 degree, cos 30 degree is root 3 by 2, right, plus P into cos 30 degree. So into 2. So 2 will get cancelled. Now net dipole moment is equal to P into root 3. Okay. So what is P? P is dipole moment, right? Dipole moment is Q into X, right? Not Q, it's 2Q into X, right? The charges are 2Q, here minus 2Q, again minus 2Q and 2Q, right? So now P is 2Q into X. Finally, the net magnitude of net electric dipole moment is 2Q into X into root 3. Okay, so the correct option here, the correct option is A. Okay, understood? Direct question, right? Here you need to find the magnitude of the P. That's it. Yeah, next question. Question number 30. Two spheres of electric charges plus 2 nanocoulomb and minus 8 nanocoulomb are placed at a distance d apart. Okay, here two spheres, right? Electric charges plus 2 nanocoulomb and minus 8 nanocoulomb separated by distance d. If they are allowed to touch each other, what is the new distance between them to get a repulsive force of same magnitude as before? Okay, so now these two spheres are brought in contact, right? So now the charge on first sphere, let's say sphere A and sphere B will be, the charge on sphere A and sphere B will be Q1 plus Q2 by 2, right? Isn't it? So Q1 is 2 nanocoulomb, Q2 is minus 8 nanocoulomb. So 2 minus 8 nanocoulomb divided by 2, which is equal to minus 3 nanocoulomb. So the charge on each sphere will be minus 3 nanocoulomb after they brought in contact with each other, okay? So now we need to find new distance, right? The force between them is same. Here minus 3 nanocoulomb and minus 3 nanocoulomb. So it is separated by distance d dash. That one we need to find, right? So now the force F dash is equal to K into Q, right? Here Q is 3 nanocoulomb, again another Q is 3 nanocoulomb. So in magnitude 3 into 10 to the power minus 9 squared divided by d dash square, okay? F is the force of attraction between these two spheres, right? So which is equal to K into Q1, that is 2 nanocoulomb, okay, Q2 that is 8 nanocoulomb, 8 into 2 is 16, right? So K into 16 into 10 to the power minus 9, right? 10 to the power minus 9 into 10 to the power minus 9, that is 10 to the power minus 18, okay? So this will be 10 to the power minus 18 divided by d square, okay? So now these two forces are equal, right, according to question. So now here K into 16 into 10 to the power minus 18 divided by d square is equal to K into 9 into 10 to the power minus 18 divided by d dash squared, okay? So now solve this, you will get d dash is equal to 3d by 4, okay? Simple mathematics, solve yourself. So d dash is equal to 3d by 4, okay? So these are the top 30 questions, okay? So if you love this video, please like and share, and if you want to watch more such videos, please subscribe. Thank you.